Namaskaram. In this session, we will discuss double integration in polar coordinates. Solution of last homework. Now we know how to evaluate a double integral over a type 1 and type 2 region. But not all regions are of this form. For example, this type of region, consider a region like this. Okay, it is clear that this region is not type 1 or type 2. Okay, so but we can evaluate double integrals over such regions using polar integration. Okay, also we know that corresponding to every point xy in Cartesian coordinate, it has a polar representation. What is polar representation? Polar representation contains two things, r and theta. And what is r? R is the distance from origin to that point, that is r. So r is always non-negative. And theta is an angle measured from positive x-axis. Okay, in anti-clockwise direction. So this is our theta. So using these two quantities, r and theta, we can represent every point in plane. And also we know there is a relation between x, y, r and theta. What is the relation? Yes, x is equal to r cos theta and y is equal to r sin theta. This is the relation between these four variables. Okay, and also one more thing. What is the meaning of theta equal to pi by 4? Geometrically, what is theta equal to pi by 4? Suppose theta equal to pi by 4 means, suppose you consider a point 1, 1. It is clear that its radius, its angle is pi by 4. Right. You think about another point 2, 2. What about the angle corresponding to 2, 2? That also the same pi by 4. Okay. So all the points belongs to this ray. Ray means the part of the straight line y is equal to x starting from origin to this side. Okay. That's why this is called a ray. Okay. So in general, theta equal to pi by 4 represents a ray like this. It's part of the straight line y is equal to x, but only this part. Clear? Okay, then there is a natural question. What is the equation of this portion of the straight line y is equal to x? Theta equal to what? Yes, its angle is this one. So theta equal to pi plus pi by 4. So theta equal to pi plus pi by 4 represents this portion of the straight line y is equal to x. Clear? So in general, theta equal to alpha and theta equal to beta represents rays like this. Okay. So now it is clear what is simple polar region. A simple polar region is a region R bounded by two rays. Theta equal to alpha is a ray, theta equal to beta is another ray, and two polar curves r equal to r1 of theta and r equal to r2 of theta. So equation of this curve is r equal to r1 of theta because radius depends theta, right? Here its radius is this one and it depends this angle, and here radius is this one that depends this theta. That's why this is called, we denote this as r equal to r1 of theta. Similarly, what about the second curve? Okay, this is r equal to r2 of theta. It is clear that here the radius is this length. That depends theta. Okay, here radius is greater than this radius. That depends this theta. That's why we denote r equal to r2 of theta represents a curve in our xy plane. Okay, only thing is this is the polar representation of the curve. That means we can define this region R like this. Alpha less than or equal to theta less than or equal to beta. That means this region. And R is varying from R1 of theta to R2 of theta. That means this region. So such regions are called a simple polar region. Okay. Also one more thing. What is geometry of R equal to 2? R equal to 2 means what? R equal to 2 means those points with this length is 2. So suppose this length is 2. Then what about this point? 2. So what is the set of all points with r equal to? It's form a circle with the center, origin and radius 2. Clear? So in general, r equal to a constant means a equation r equal to constant represents a circle with the center, origin and radius c. Clear? Okay, now we are ready to define another one, that is called polar rectangle. Polar rectangle is a simple polar region for which the bounding polar curves are circular arcs. That means two sides are bounded by rays, and instead of here we can use general polar curve. Here instead of general polar curve we use circular arcs. Okay. That's the difference. So two rays and two circles. So a region like this type of regions are called polar rectangle. Okay, suppose we have to find a double integration over a region like this, a simple polar region. So here region is in terms of r and theta because it's a simple polar region. So naturally our surface z is equal to r and theta. In Cartesian coordinates our function is like f of xy. So here our region is in terms of r and theta. So our surface is also in terms of r and theta. Okay. We have seen that in Cartesian coordinates we divide the region as small rectangles. Here it is polar coordinates, so we divide the region as small polar rectangles instead of normal rectangles using circles and rays. And we consider only the polar rectangles which is completely inside the region R. So this green boundary is the region R, and we consider the only polar rectangles which is completely inside R, similar to our Cartesian system. Okay, we know that the meaning of double integral. Double integral over R, f of r theta dA, that is equal to limit n tends to infinity sigma k equal to 1 to n f of r k star theta k star delta a k. Okay, and suppose this region contains only n such polar rectangles, and also we choose this r k star theta k star as the center point of the polar rectangle. Okay. Okay, it is clear that this you consider the one term f of r1 star f of rk star theta k star and delta k. This is nothing. This is the volume of this yellow solid shape. It's like a parallelepiped, but here its base is not a rectangle. It's a polar rectangle. Okay, and if you take the sum of all such volumes, that is approximately volume of this region, and the approximation is better if n is very large. That's all. Okay, so now only headache is how to evaluate delta ak. In the case of Cartesian coordinates, it is clear that all are small rectangles. If you know the length is delta xk and height is delta yk, then we know delta ak equal to delta xk into delta yk in the case of Cartesian coordinate. But here the case is different. Here this is not exactly a rectangle. It's a like a polar rectangle. Okay, so next we have to evaluate the area of this polar rectangle, or we have to evaluate delta ak in terms of r and theta. Okay, for evaluating this delta ak, we consider a kth polar rectangle, this or kth polar rectangle, and we choose rk star theta k star as the center point. Okay, that means this length is rk star. Clear? This length is rk star, and this angle is delta theta k. Clear? So this angle is delta theta k. This length is rk star. Okay, it is clear that area of this the small polar rectangle is area of this big sector minus area of this small sector. Okay, then how to find area of a sector like this? Here argument is theta, this angle is theta, and radius is r. Then how to find the area of this sector? Yes, its area is theta by 2 into r square. So this is the area of a sector like this. So how to find area of this blue region? Okay, also we assume that here this difference is delta rk, and this is the center point. So it's half. This is half delta rk, this is half delta rk. So we assume that this big radius is suppose r1 and this small radius is r2. This is r1 and this is r2. Then what is the value of r1 in terms of this rk star and rk? It's clear that r1 is equal to rk star, that is this length plus this portion, that is 1 by 2 delta rk. Clear? And similarly, what is r2? This radius is rk star. So this is rk star minus this length, half of delta rk. So 1 by 2 delta rk. Clear? Now the radius of two sectors are clear. Then you can use this formula and take the difference. This gives this area. So what is delta rk? Delta ak. So the area of big sector is theta by 2, that is this is delta theta k by 2 into this big radius is rk plus delta, oh this is delta rk by 2 square minus area of this small sector, its radius is its theta is remains delta theta k, so delta theta k by 2 into rk minus this small radius, that is half delta rk by 2 whole square. Now you can expand these two brackets and simplify. This expression become, so delta ak equal to rk star delta rk delta theta k. So now area in terms of r and theta, you can substitute in this formula. So this become limit n tends to infinity sigma k equal to 1 to n f of rk star theta k star. This delta ak become rk star delta rk delta theta k. So what is the analogous notation or analogous notation of double integral as similar to our double integral in x and y? In our Cartesian coordinates, delta ak only delta xk delta yk. So we use only dx dy or dy dx. Okay, here instead of delta rk delta theta k, one more thing rk star. So what is the analogous representation? So the analogous representation is integral alpha to beta and r1 theta to r2 theta f of r theta into r dr d theta. So here our dA become r dr d theta, not dr d theta, r dr d theta. Okay, so it is clear that here actually this is the range of r. R is varying from, you can think this is like a strip. You can think this is the lower value of r and this is the upper value of r. So you think a strip like this. Okay, you have to cover this entire region. To cover entire region, theta should varying from this alpha to beta. Clear? So that means strip is moving like this in this direction and cover this region. So here theta is varying from alpha to beta and radius is moving from r1 of theta to r2 of theta, f of r theta. The only difference is instead of dr d theta, here we use r dr d theta. Clear? Okay. Okay, consider a problem. Evaluate double integral over r sin theta dA, where r is a region in the first quadrant, that is outside the circle r equal to 2 and inside the cardioid r equal to 2 times 1 plus cos theta. Okay, so first we have to a rough sketch of this region. Okay, first we have to plot r equal to. What is r equal to? It is clear that it's a straight, it's a circle with the center origin, radius 2. Okay, so r equal to is a circle like this. And next we have to plot r equal to 2 times 1 plus cos theta. Okay, so we know this is the graph of cos theta in the interval 0 to 2 pi. So cos theta is decreasing up to pi. Okay, so when theta equal to 0, what is the value? Its value is 1, so this is 2, so r equal to 2 into 2, that is equal to 4. So when theta equal to 0 means positive x-axis. When theta equal to 0, r value is 4, so this is the point. Clear? If theta is increasing, what happened? Our cos theta is decreasing. So 1 plus cos theta also decreasing, 2 times 1 plus cos theta also decreasing, r also decreasing. Okay, and what is the value of cos theta when theta equal to pi by 2? When theta equal to pi by 2, cos theta equal to 0. So when theta equal to pi by 2, r equal to 2, right? So radius is continuously decreasing and reach the point 2. Okay, theta is increasing, radius is decreasing and touching at the radius 2. Then after pi by 2, what happened? Again, if theta is going to pi, so this cos theta is negative. That means cos theta is decreasing. So radius is again decreasing, and ultimately when theta reaches pi, radius is 0. Why? When theta equal to pi, cos pi is minus 1, that is 0. So it is almost like this. And when theta equal to pi, radius is reduced and tending to 0. Then after pi, what happened? Again, when theta is greater than pi, cos theta is increasing up to 2 pi. Okay, so the same shape, it going like this, touching this point and radius is 4. When theta equal to 2 pi, radius is when theta equal to 2 pi, cos theta equal to 1. So again radius is 4. Okay, almost this is the shape of the cardioid. And what is our region? Our region in the first quadrant, outside the circle and inside the cardioid. So which is the region? Yes, this region. So we have to integrate over this region. Clear? Okay, this is the exact shape of the curve. So we have to integrate over this one. So next you have to set up this integral, set up the limits. Okay, this integral is equal to double integral sine theta. What is dA? Instead of dA, it is r dr d theta. So what is the change of r? Change of r in terms of theta. So it is clear, you consider a strip like this. That's all. You consider a strip like this. And what is the lower value of r? That is from the circle. That is r equal to 2. And what is the upper value of r? That is from the cardioid. That is 2 times 1 plus cos theta. So here r1 of theta is throughout 2. r2 of theta is 2 times 1 plus cos theta. Clear? And to cover this blue region, what is the range of theta? Theta should varying from 0 to pi by 2. Clear? So 0 to pi by 2. So this is the setup of this integral. Now you can integrate. So first you integrate with respect to r. So this become r square by 2 and 2 to 2 plus 2 into 1 plus cos theta. Then you substitute upper limit and lower limit for r. So this become, so this is equal to sine theta into 4 times 1 by 2 is common, you can take outside. So 4 into 1 plus cos theta square minus, when r equal to 2, this will become sine theta into 4. Okay. Here 4 is common, you can take outside and you can cancel. So this will become 2 times. Okay, this becomes 0 to 2 pi 1 plus cos theta square into sine theta d theta minus integral sine theta d theta. Okay, for integrating this portion, if you substitute u equal to 1 plus cos theta, then du equal to minus sine theta d theta. So sine theta d theta become minus du. So 1 minus sign is there, and this become integral u square. That is integral u square is u cube by 3. So minus of u cube by 3. And what is u? 1 plus cos theta. Okay, so this integral become minus of 1 plus cos theta whole cube by 3, and this is minus cos theta, and we have one more minus sign. This become plus cos theta, and both the limits are same, so 0 to pi by 2. So next we substitute upper limit and lower limit. Yes, when theta equal to pi by 2, this is 0, cos pi by 2 0, so minus 1 by 3. This is 0 plus 0 minus, when theta equal to 0, cos 0 is 1, so this is minus of 2 cube, that is minus 8 by 3 plus cos 0 is 1. Okay, then you can simplify. Upon simplification, this become 8 by 3. Okay, so this is the value of this integral, 8 by 3. Okay, this answer is 8 by 3. Next problem, use a polar double integral to find the area enclosed by 3 petaled rolls r equal to sine 3 theta. So first we have to draw a rough picture of r equal to sine 3 theta. Okay, so here r equal to sine 3 theta. So theta is actually theta, to plot this polar curve, theta is varying from 0 to 2 pi, right? If theta is varying from 0 to 2 pi, what about 3 theta? 3 theta is varying from 0 to 6 pi. Okay, so in the interval 0 to 6 pi, our sine theta or sine 3 theta, the behavior of sine 3 theta when theta is varying from 0 to 2 pi is like this. Okay, so what about this point? Okay, this is pi. Okay, so 3 theta equal to pi means what about theta? Theta equal to pi by 3. So 3 theta, when theta is pi, whenever, sorry, 3 theta equal to pi whenever theta equal to pi by 3. So whenever theta equal to, suppose this radius is pi by 3. So whenever theta equal to pi by 3, our r is 0. Then r is negative. After theta crossing this pi by 3, this angle is pi by 3. After theta crossing this pi by 3, our r is negative. Clear? So there is no such point in polar coordinates, because in polar coordinates we know that if you suppose this is a point, then we know that it has two values r and theta. R is this distance, so r is always positive. So if r is negative means there is no such point. Okay, so you can plot only points if r is positive. So r equal to sine 3 theta is positive in this interval and also this interval. So we have three different intervals. Okay, so in terms of theta, this is corresponding to 0 less than or equal to theta less than or equal to pi by 3, right? So in the interval 0 to pi by 3, we have a curve. What is the shape of the curve? R is gradually increasing and reaching a maximum of 1, then decreasing to 0. So what about the curve? So when theta equal to 0, r equal to 0, radius value 0. When theta is increasing up to this point, r is increasing and reaching a maximum value, then come back to 0. When theta equal to pi by 3, r is again 0. What about this point? This point is actually pi by 2 for 3 theta. So for pi, it is pi by 6, right? So this ray, suppose we consider a ray theta equal to pi by 6. So when theta equal to pi by 6, r reaches its maximum of 1, this length is 1, then come back to 0. Okay, then what about this point? This point is 2 pi. So 3 theta equal to 2 pi means what about theta? Theta is 2 pi by 3. Okay, so when theta reaching 2 pi by 3, suppose this is our 2 pi by 3. When theta reaches 2 pi by 3, again r is starting, we can plot the points because r is 0 and increasing and r is positive. Okay, and so if 3 theta is in between 2 pi to 3 pi, r is positive. That means theta is in between 2 pi by 3 to pi. When 3 theta equal to 3 pi means theta equal to pi. So suppose this argument is 2 pi by 3. Then we know that this argument is pi. So in between these two, we have a curve like this. Okay, same size. This is not like this, same size, because this maximum radius is again 1. Okay, so similarly when 3 theta crossing 4 pi, again r is starting to positive up to 5 pi. So 3 theta equal to 4 pi means theta equal to 4 pi by 3, and this is 5 pi by 3. So with theta in between 4 pi by 3 and 5 pi by 3, we have a curve. And what about the maximum? The maximum at this point is actually 4 pi plus pi by 2, right? That means 9 pi by 2. So 9 pi by 2 means what is the corresponding value of theta? By 3, that is 3 pi by 2, right? So maximum reached, the curve r is reached maximum value when theta equal to 3 pi by 2. 3 pi by 2 is nothing, this negative imaginary axis. So curve is almost like this. Okay, after that again r is negative, there is no graph. So our graph is like these 3 petals. That's why this is called a 3 petal rose, and this length is 1 for all the petals. Okay, okay, this is our exact shape of this curve. So next we have to find the area. We know how to find area using double integration. So we know that area is equal to double integral r 1 dA. So in polar coordinates, this is double integral 1. What about dA? dA is r dr d theta. So next we have to find the limits. And one more thing, here the area of 3 petals are same. So better you consider the area of 1 petal into 3 times. So this area equal to 3 times area of 1 petal. Okay, so that is double integral. And what is the range of r? R is always starting from 0, clear? R is always starting from 0 up to this end. So what is the equation of this end? That is sine 3 theta. So r is varying from 0 to sine 3 theta. And to cover this petal, theta is varying from this point to this point, clear? And we know this is theta equal to pi by 3. So this is 0 to pi by 3. This is enough. So 3 times 0 to pi by 3, 0 to sine 3 theta, 1 r dr d theta. So this is the setup of this integral. You can evaluate this integral. And this is equal to integral 3 times 0 to pi by 3. Integral of r is r square by 2, 0 to sine 3 theta d theta. So 1 by 2 is common, you can take outside. 0 to pi by 3 sine square 3 theta. When r equal to 0, this time equal to 0. Okay. So next we have to evaluate the sine 3 theta with respect to theta. So we know that sine square theta is equal to 1 minus cos 2 theta by 2. So this is 1 minus cos 6 theta by 2 d theta. So you can take outside 2. This is 3 by 4. 1 minus cos 6 theta d theta. Now you can integrate with respect to theta. So this become, so theta minus sine 6 theta by 6. This is pi by 3 minus when theta equal to pi by 3, this is sine 2 pi by 6 minus when theta equal to 0, this is 0, sine 0 also 0, and sine 2 pi is also 0. So this is, you can cancel these 3. So this become pi by 4. So the area of this 3 petal rose is pi by 4. Together these 3 petals. Okay. Yes, answer is pi by 4. This is your homework. Thank you.